Today, I would like to talk about several efficient reduced order models. I will be talking about multiple concepts. They include linear and nonlinear manifold solution representations, framework called LaSDI, and the intrusiveness of the data-driven approaches, physics constraint methods, and component-wise reduced models for multi-scale problems. All right, before I dive into the main presentations, I would like to recognize wonderful reduced order model teams at Lawrence Livermore National Lab, whom I was fortunate enough to work with. Plus, without these internal and external collaborators, I wouldn't be able to present what I am presenting today. So big thanks to all of them. All right, physics simulations play an important role in modern science. I do not think anyone here will have an objection to what I have just claimed. If the physical simulations were not important, the concept of digital twins would not have emerged. So we can easily agree on the fact that physical simulations are important, but then what is the problem? Well, they can be extremely expensive computationally, as demonstrated in this slide, taking 1 hour or even weeks when using the high-performance computing machines. This is unfortunate for many decision-making applications, such as design optimization, uncertainty quantification, and inverse problems, because there we need to run these four physical simulations many times as we explore parameter space. Therefore, we need a fast simulation capability, and we will achieve this goal using data. Well, and then how can we accelerate the existing physical simulations with data? The most straightforward way would be to use a neural network to directly relate input and output data. For example, we have trained a conditional generative adversarial neural network to relate permeability and pressure fields for porous media flow simulations. We were able to get very accurate predictions and a high speed up. However, this is a black box approach because we blindly relate input and output data with some neural network structure, which we do not have much control on and which we do not understand deeply. So once the neural network is trained with some given data, it is what it is. In that sense, it lacks interpretability and explainability simply because this neural network structure is not familiar enough to us yet. Well, then how can we get an interpretability? We have to somehow relate this data-driven model with what we are familiar with already, the things we have studied for a long time. For example, ordinary differential equations or partial differential equations. To illustrate that, let me consider a simple radial advection problem, which is described by a well-known partial differential equation. You solve it using some numerical schemes such as finite element or finite difference methods, then generate simulation data. This data is high dimensional, so it would be hard to fit them directly into some model. Plus, remember that our goal is to build a fast model. To build a fast surrogate model, we better deal with reduced space dimension. So we compress the data, which, for example, leads to the latent space dynamics with dimension of only 3. As depicted with this trajectory graph, there are two different types of compression techniques, linear compression and nonlinear compression. Either one has some pros and cons, which I am going to lay out later, but this low dimensional data is a lot easier and more manageable to fit into a model. Which model would you use? We can imitate what Isaac Newton did with orbital motions. Yes, differential equation. We can fit the latent space data into differential equations. For example, linear ordinary differential equations or quadratic differential equations, even some nonlinear functions such as exponential or the logarithmic functions and so on. Then you can solve these little ODEs to predict the solutions very fast. Let's call this procedure LaSDI, which stands for latent space dynamics identification. By the way, if we choose to use linear compression such as SVD and the linear differential equation for latent space dynamics model, then we are more or less using the famous method that is dynamic mode decomposition, so-called DMD. On the other hand, if we use, again, linear compression and polynomial ODEs, mainly quadratic ODEs for latent space dynamics model, then we are again using the famous operator inference method. By the way, we know a lot more about ODEs than neural networks. So this approach is, although purely data-driven, it is interpretable. For example, if we happen to know this A hat matrix right here, right, A hat matrix explicitly, we can perform eigenvalue decomposition and write an analytical solution for linear ODE in terms of eigenvectors and eigenvalues. For example, if the real part of the eigenvalue is greater than 1, then the solution will explode. Therefore, we should make sure that the eigenvalue does not exceed 1 if we know that the true solution does not explode. Here, eigenvalue serves as an indicator which tells us why the model fails if it fails, why the model it was successful if it was successful. So it is interpretable and explainable approach. Now we want to make this LaSDI framework robustly accurate when the parameter changes. There are many different ways of making the framework parametric. First of all, we only want to deal with latent space model, not the full model, which implies that parameterization must be done within the latent space. Let me show you one way of doing it. Here is a parameter space D for each training parameter point. For example, parameter point mu1, we can build a tailored ODE that best describes the latent space dynamics at that point. Note that the coefficient matrix A hat depends explicitly on mu1. We can do the same thing for mu2, mu3, and mu4 and mu5, and so on. Then we can interpolate the linear coefficients of the ODE for a test point mu star. Note that the coefficient matrix A hat for the mu star depends explicitly on the testing parameter mu star as well as all the training points. As you can easily imagine, you can apply similar interpolation for other testing points. We have applied the LaSDI framework to the radial advection problem by parameterizing initial condition with two frequency values W1 and W2. For this problem, we took uniformly sampled training points as shown in this graph 5 by 5, which gives 25 training points in total, which is depicted by the rectangular here. For each training point, we generated the high-dimensional simulation data. Then we compressed them to a latent space with dimension of 3 using autoencoder, which is nonlinear compression technique. Then the coefficient of ODEs that fits the latent space dynamics data were interpolated for the parameterization. This heat map shows the relative error on a given parameter space. The maximum relative error was 5.4%, which occurs around here. The LaSDI framework was able to give us a speed up of 200x when compared to the full model simulations. Decent results, right? But we were not happy about the high relative error concentrated on the particular region of the parameter space. For this particular problem, it seems to happen on the right side of the parameter space right here. This was caused by the uniform sampling. We needed a better sampling procedure, possibly by incorporating physics information. We have actually developed such a non-uniform sampling procedure that is guided by the underlying physics. When we applied it to the same radial advection problem, we got better accuracy, even though we used the same number of training points, that is 25 training points in total. The heat map on the right shows the relative error distribution on the parameter space when the physics-informed greedy sampling is used. As you can see, the training points were not sampled uniformly. More samples were chosen on the right bottom corners, which makes sense because the relative error with the uniform sampling were high on those right bottom corners. With this physics-guided non-uniform sampling, method. With this physics-guided non-uniform sampling method, we were able to achieve a maximum relative error of 2%. This time, the maximum relative error happens on the left side of the parameter space. So how do we do it? We followed an active learning paradigm where you adaptively append training data while the autoencoder is being trained. For example, you start with 4 corner points in the parameter space, which were marked by 4 empty squares where we run simulation data. Then we check if the number of training points reach the maximum allowed. Let's say we are willing to spend 10 training points in total. Since we only have 4, we are going to move on to the training of the autoencoder and dynamics identification process. Because the autoencoder and the dynamics identification steps must communicate with this adaptive sampling procedure, we combine the latent dynamics identification step into the autoencoder training by adding the latent space dynamics regression terms as loss function terms. So there are 3 terms in total in the loss function. The first one is the typical reconstruction loss of autoencoder, which is depicted here, which takes the difference between original high-dimensional simulation data with reconstructed one through encoder and decoder. The second and third loss terms, which is written here, are related to the latent space dynamics regression terms. We go through several epochs to train the neural net, train the autoencoder, say 2000 epochs to minimize these 3 loss terms simultaneously with the current training data. Then we go back to sampling where we apply random validation points. At each validation point, we compute physics-informed error indicator. We find out where the maximum physics error indicator occurs with the current autoencoder and the dynamics identification model. In this picture, this red point gave us the maximum error. So we take it as a training data and generate the simulation data there and add it to autoencoder training. We repeat this process until the desirable accuracy or the maximum number of training points are reached. If you want to know more details about this physics-informed greedy sampling procedure, you can check out this paper down there. Or I have a short YouTube video that explains it. You are welcome to check it out. It's less than 10 minutes, so I am sure you will enjoy it. All right, enough for non-intrusive methods now. How about physics-constrained data-driven approach? If you can somehow incorporate the physics in your data-driven method, it will be for sure interpretable. And that would be the most desirable things because it will be easier now to preserve some underlying structures such as conservation, symmetry, and positivity. To discuss that, let's go back to the page where I described the process of compressing high-dimensional data. Again, after the compression, you get the latent space dynamics data with a reduced dimension. The interpretable data-driven approach was to fit these data into a user-defined ODE. Well, instead, what if you derive a system of ODEs that describes the latent space dynamics data from the original governing equations? Is it even possible? The answer is yes. One way of building such a system of ODEs for latent space dynamics is given by traditional projection-based reduced order model. To explain it, let's start with this governing equations, represented by the ordinary differential equation. You can consider it as a semi-discretized version of the partial differential equations that describe your underlying physics. Here, W is a state variable, F is a nonlinear function, and T is the time variable, and mu is a parameter. We first approximate the solution as a linear combination of reduced spaces phi, whose dimension is a lot smaller than the full order model dimension big and sub S. Then you plug this solution representation into the governing equations, you will end up with an overdetermined system where you have more equations than unknowns. So to close the system, you apply some kind of projection. Here I have applied the Galerkin projection that gives a reduced system of ordinary differential equation. By the way, this ordinary differential equation describes the latent space dynamics, which was completely derived from the original governing equations that describes the underlying physics. So this is physics constrained or physics informed latent space dynamics discovery approach. Then you can apply your favorite time integrator to this reduced system. For example, the backward Euler time integrator has been applied here just for the demonstration purpose. This gives us the fully discretized reduced nonlinear system of equations you have to solve in every time step. Of course, we have to deal with this nonlinear term through the hyperreduction but let me skip that part for now. The history of the projection-based reduced order model development is rich. It has been successfully applied to many different applications. For example, we were able to extend the traditional projection-based reduced order model to time windowing approach and applied it to several Lagrangian hydrodynamic problems. Here you are looking at the cases where the reduced order model achieves a speedup of 14.6 to 87.8. with an indistinguishable accuracy level that is a relative error less than 0.1%. There are many variations of projection-based reduced order models. For example, the solution does not always have to be represented by a linear combination of reduced bases. It can be completely nonlinear. As it is depicted in this slide, the decoder neural network can be used as a nonlinear manifold solution representation, G. Well, by doing so, you are adding more nonlinearity to the nonlinear system of equations you have. So the hyperreduction becomes really important here. So when you apply the hyperreduction on the neural network, the structure of the neural network is really important. Just to demonstrate that, let's imagine that these three outputs are the points you would like to evaluate throughout the hyperreductions. And look at the hidden nodes which are connected to those three outputs. And as you go from layers to layers, the number of hidden nodes connected to those outputs are increasing exponentially. This is causing the bottleneck when you actually compute the Jacobian of the neural network, which is required for the nonlinear manifold reduced models. Instead, we chose to use the shallow neural network, which is sparse structure. By doing so, the number of hidden nodes connected to the selected outputs for the hyperreduction is not increasing exponentially. So the computation of the Jacobian of the neural net can be done as efficient as possible. This is how we achieve the efficiency of the nonlinear manifold reduced models. Here we compare the performance of different types of surrogate models that I have introduced in this presentation. FORM is full order model, NMROM is nonlinear manifold reduced order model, LSROM is linear subspace reduced order model, and deep fluid is a type of black box approach. As you can see from the movies, NMROM and full order model are almost identical in IBOM norms, although NMROM used a latent space dimension of only 5. Quantitatively, NMROM achieves less than 1% maximum relative error. Furthermore, a speedup of 11 is achieved by the NMROM thanks to the hyperreduction, while LSROM and deep fluids are struggling to achieve a precise solution, giving 34.4% relative error for LSROM and 38.6% relative error for deep fluids, which is not good enough for most scientific applications. Physics-constrained projection-based reduced order model have also been successfully applied to accelerate design optimization process. For example, here is a numerical demonstration for lattice-structure design using component-wise reduced order model. Here we minimize the compliance, imposing a constraint of mass being at most 40%. The downward pressure force is applied to the top middle port. Dirichlet boundary conditions are imposed at the bottom corners. The full order monolithic finite element solve involves 2.7 million degrees of freedom for this particular problem, while component-wise reduced model has only about 4,000 degrees of freedom. The movie shows the optimization history from the beginning. Initially, it started with a uniform density variable and evolves into an optimal design where blue component implies no materials there, while red component implies that you put materials there. With component-wise reduced order model, a speedup of 660 was achieved and a tunable accuracy from a relative error less than 1% down to 10 to the negative 8 was also achieved, which is pretty good. The component-wise reduced order model lattice structure design can be applied for stress constraint problem as well, where the mass is minimized with stress constraints. This is considered a harder problem than the minimizing the compliance problems. Here we achieved a speedup of 150 times with component-wise reduced order model with less than 5% relative error in stress measure. This is quite an achievement because it is usually hard to obtain an accurate stress measure with surrogate models for lattice structures such as homogenization-based method or beam or truss-like structure. As you can see from this zoomed picture, component-wise reduced order model is able to bring high fidelity accuracy for stress quantity apply everywhere in the computational domain. The component-wise reduced order model has a great potential to speed up multi-scale problems. All right, so much for physics-constrained projection-based reduced order models. Let me conclude the talk with some advertisements. If you are interested in generating the numerical results that I have shown you today, you can use our open source software tool for data-driven physical simulations, that is libROM, which you can find it from this GitHub page. Also, useful documents and examples are given in libROM webpage, that is librom.net. So please check it out and take advantage of it. With that, let me conclude my talk. Thank you so much for your attention, and any questions are welcome.